All right, kids, here we are, Stats with Glenn. Can you believe we're up to chapter 10? Is that just mayhem or what, kids? We made it. Chapter 10. Chapter 10 is an introduction to t-tests. T-tests are among the most commonly used real tests. So chapters 6, 7, 8, and 9, we're really building up to an understanding of hypothesis testing. T-tests are sort of actual real hypothesis tests that statisticians and researchers use regularly. So all those chapters are kind of building up to this moment. Do you feel it, kids? This is it. So here's the deal. A defining feature of a t-test is one where you estimate sigma. Seems like a weird way to start, but we're going to start right there. We're estimating sigma. Remember that sigma is your population level standard deviation. In the real world, we often do not have population level standard deviation. We are often required to estimate population level standard deviation. So there's three different kinds of t-tests that we're going to go over in the next couple of chapters. In each of them, we are estimating population level standard deviation. It's kind of a hallmark of the t-test. The first t-test that we're going to go over is called a one-sample t-test. With a one-sample t-test, we are doing something very similar to what we have been doing with hypothesis testing with the z-test, except now we're estimating sigma. So an example is when you have mu sub 2 is known, sigma sub 2 is not. And you are comparing a mean from one sample with some known population mean. So you're comparing a mean from one sample with a known population mean. So here's an example. Suppose that the mean for the general population for GPA is 2.5. And suppose that you want to see if students in your dorm are somehow significantly better in terms of GPA than the general population. So I'll give you some given information. Let's say that alpha equals 0.05. And let's say you get data from 3 random students in your dorm. And let's say that you get someone has a 3.0, someone has a 3.2, and someone else has a 3.1. So that's the data from the 3 randomly selected people from your dorm. What we want to see is whether the mean representing this sample, representing the population of people in your dorm, is significantly greater than the mean for the general population. So here are the steps, and you'll see where the steps differ a little bit from what we've been doing. Step number 1 is going to be h sub 1 and h sub 0, just like we've been doing. So here, mu sub 1 is going to correspond to students in your dorm, and mu sub 2 corresponds to the general population. This part is no different than what we had done in the prior chapters. H sub 1, mu sub 1 is greater than mu sub 2. In other words, the population mean GPA for my dorm, or your dorm, is predicted to be greater than it is for the general population. The null hypothesis follows the same policies that we've been doing. It's the opposite, and it includes equal signs. So mu sub 1 is less than or equal to mu sub 2. So far, so good. No changes. Step number 2 is going to be a little bit different. Step number 2 is going to be the comparison distribution. And a comparison distribution is now going to be a t distribution. A t distribution approximates a normal distribution. It is like a normal distribution, except it has what we call, quote, fatter tails. And it varies as a function of the n, which is the sample size. Okay, so here are 3 potential t distributions. Here's an n of 3, which is what we're actually going to be working with because we have an n of 3 in our sample. An n of 3 is going to be a t distribution that's like that. It's really flat and it has very what we call fat tails. As the n gets higher, like with an n of 10, it starts to look more like a normal distribution. And as n gets even higher, the t distribution will start to approximate even more a normal distribution. So your t distribution, which is your comparison distribution, differs as a function of the n, or of your sample size. Now here's a way to think about what it's doing. If your sample size is really small, remember inferential stats is about trying to make an inference to a more general population. If your n is really small, that's kind of saying, I don't trust you. I don't trust your data. I don't trust your ability to make that inference. If you're trying to make an inference about your entire dorm, let's say it has 300 people, and you have data from only 3 people, I'm going to give you a comparison distribution where the tails of the distribution are really spread out, where your critical value is really far from the mean. I'm going to make it hard for you to reject the null hypothesis because I don't trust your small n. As your n gets bigger, your distribution is like, well, that's a bigger n, so let's look a little more like a normal distribution, which will have the effect of making it slightly easier to reject the null hypothesis. And then if you have a really big n, it's like, whoa, you got an n of 1,000? Thumbs up to you. We're going to give you something that looks just like a normal distribution, making it easier for you to reject the null hypothesis. So that's why the comparison distribution in a t distribution is very sensitive to the n, or the sample size. Here, the comparison distribution is a t distribution based on an n of 3. Step number 3. Now in a t distribution, just like in a z distribution, in t units the mean is 0. So we can put the mean at 0. Step number 3 is going to be t critical. Just like we had z critical, now we have t critical. T critical. T critical is actually going to be based on a table in the back of the book, Appendix B. which is on page 329. Okay, so here's Appendix B right here. The T critical is determined by 3 parameters. One is the degrees of freedom. Degrees of freedom, it's a little complicated as to why this is called the degrees of freedom, but degrees of freedom equals n minus 1. Simple formula. So n is 3, so degrees of freedom is 2. Now, then you go by if you have a one-tailed test or a two-tailed test. Remember, if you have a prediction in a specific direction, you have a one-tailed test. Here, I'm predicting that students in my dorm have a mean that is higher than students in general. So I'm going to be looking at the one-tailed tests only. And then you go by alpha, which could be 0.1, 0.05, or 0.01. And the answer here is 0.05. So the one number that corresponds to all those parameters being true is 2.92. And it's positive because mu sub 1 is predicted to be greater than mu sub 2. And you'll see that that means that we're looking at the right side of the distribution. Okay, so T critical equals 2.92. Okay, and again, that's from Appendix B from the book, and that's how you do it. You go by the number of tails, 1 or 2-tailed, the alpha, 0.1, 0.05, or 0.01, and the degrees of freedom, which is simply n minus 1. So T critical is 2.92. I'm going to label that here. On my comparison distribution. So T critical equals 2.92 over here. You can see where this is going. We're eventually going to compute T, or what I'll call T obtained. Nothing happened, kids. Everything's fine. Statistically, everything's fine. We're going to compute T. We're going to compare T with T critical, and this is our alpha region over here. So we're going to see if T obtained is more extreme than T critical. Same kind of process that we've been doing. Step number 4, we're actually going to compute T. Okay, so T equals a particular sample mean minus mu sub m sub 2 divided by S sub m. Okay, we've seen all this stuff before except for S sub m. S sub m, or we might want to call it S sub m sub 2, it doesn't really matter, but it is an approximation. S sub m sub 2 is an approximation of sigma sub m sub 2. Okay, so we don't have sigma. We're not given the population level standard deviation. We don't have sigma sub m sub 2. So now we're going to create S sub m sub 2, which is an estimate of sigma sub m sub 2. So this is one of the defining features of what we're doing with a t-test. Okay. So we need to get S sub m sub 2. Okay, and we're actually going to do that with our raw numbers. So remember we had was that 3.0? Did I start with that? What were the numbers I started with? I just erased it. I think I had 3.2, 3.0, and 3.1.
3.1.
Okay, not sure if that was the same exact order.
That wasn't the order, but I think those are the right numbers.
Those are the right numbers, so we're going to be fine. We're going to be fine. Okay, so now we need to compute indices of standard deviation to be used for the t-test based on this information. This is going to be based on the processes that we used going all the way back to the earlier chapters. So we're going to subtract out the mean. The mean here is 3.1. X minus m, that's going to be 0.1. That is negative 0.1, and that is 0. X minus m squared. Okay, we're doing all this so that we can get s sub m sub 2, by the way. X minus m squared is 0.01, 0.01, and 0. Okay, sigma x minus m squared is 0.02. Okay, things are about to change a little bit. The next thing that we're going to compute is s squared. S squared is an estimate of sigma squared, and it equals sigma x minus m squared divided by n minus 1. It's not divided by n, but it's divided by n minus 1. It's as if it's like the average of that column, except we're dividing by n minus 1 instead of n. That makes the denominator lower, which makes the estimate higher. And the reasoning there is that your actual population level standard deviation and variance are higher than it's going to be in a sample. And to adjust for that, instead of dividing by n right there, we divide by n minus 1. If that's too complicated for you to think about, just realize this is the formula. S squared is sigma x minus m squared divided by n minus 1, which is 0.02 divided by 2. Which is 0.01. And then the next thing that we're actually going to compute is going to be s squared sub m. So we can compute s. S is the square root of s squared, which in this case is 0.1. But I'm going to put that as a sidebar, because s is actually not going to be computed in t. Remember, t equals m minus mu sub m sub 2 divided by s sub m sub 2. S is not used in those calculations. S will be used later. S is our best estimate of sigma, or our best estimate of the population level standard deviation. But the next thing that we're going to compute is s squared sub m. Remember, once n is greater than 1, we're dealing with distributions of means, and t distributions are special versions of distributions of means. So the standard deviation of our t distribution is going to be s sub m, or s sub m sub 2, which is the standard deviation of a distribution of means. So s squared sub m equals s squared divided by n, which equals 0.01 divided by 3, which is, here I have 0.00, too small, I'm going to put that as 0.003, and then s sub m equals the square root of s squared sub m, which in this case is 0.06. So T equals our sample mean minus the mean of the distribution of means divided by S sub m sub 2, which in this case is 0.06. So that equals 3.1 minus 2.5 over 0.06. Which is 10?
Yeah.
10. Whoa, that's a whopper, kids. 10. Okay, so let's take a look at what that means. Okay, so that was step number 4, computing T. In step number 5, we're going to comment on the null hypothesis. Okay, so here's my T distribution. My T critical is 2.92, and my T obtained equals 10. So 10, if you look at my alpha region, which is over here, 10 is way more extreme than my T critical. And what that's saying is that I have rejected the null hypothesis. Okay, so that's my final bit here, comment on the null hypothesis. I've rejected the null hypothesis in a very big way. My obtained T-score was much more extreme than my T-critical. I provided really strong evidence that students in my dorm are doing academically much better than students in general or students on average. So that's how we would interpret that. The other thing that we can do is compute effect size. So effect size is still Cohen's d. And it equals m minus mu sub 2 divided by s, which is our estimate of sigma. Okay, so it's looking at my mean compared to the mean of my general population relative to my estimate of the population level standard deviation, which in this particular case is 3.1, absolute value 3.1 minus 2.5 divided by 0.1. Which is actually 6. So you remember effect size conventions, 0.2 is small, 0.5 is medium, 0.8 is big, 6 is huge. Okay, so why did we reject the null hypothesis so hard before? Partly because we had such a big effect size, which meant we had a powerful design. So that's the one sample t-test. The other kind of t-test in chapter 10, is that what we are?
Yeah.
Chapter 10? Crazy. The other kind of t-test in chapter 10 goes by a couple different names, but we'll often call it a within group t-test. Okay, with a within group t-test, students sometimes find the hypothesis framing a little bit confusing, so I'm going to try and address that straight away. And we're going to start right away with an example. So a lot of times with a within group t-test, you're looking to see if within the same group of people, there's a difference between scores on one variable versus another variable. Very common, we will think about this in terms of what we call a pre-test versus post-test example. So you might think of a special diet. So here's a special diet, and here's people's scores at time 1, so this could be their weight, and this could be their scores at time 2, their weight at time 2. And let's say, I'm gonna start with data here. So let's say the first person went from 120 pounds to 100 pounds. The next person went from 200 pounds to 160 pounds. And the final person went from 140 pounds to 100 pounds. Okay, so that's a classic within group t-test design or situation, and it's often used for a pre-test, post-test. You want to see if some intervention led to some kind of change, either higher scores or lower scores. We're going to start with the hypothesis test, or the hypothesis articulation, H sub 1 and H sub 0. It's going to be a little bit different, okay? So with a within group t-test, we're going to look at differences. And then we're going to look at something that we call D bar, which is the average of those differences. Now, I'm going to introduce you as a little bit of a sidebar, but it's pretty important. I'm going to introduce you to something called D bar cap. D bar cap, remember cap statistically means predicted. So D bar cap means the predicted average difference. Okay, so D is difference, 120 minus 100 is 20, that's a difference. Eventually we're going to get D bar, which is going to be the average of the differences. And D bar cap is the predicted average of the differences. Remember we talked about the difference between whether something was predicted or whether something was actual. So what's important here is this is actually predicted. So if we look at our hypothesis, the hypothesis is that scores at time 1 will be lower compared with scores at time 2. And if scores at time if scores at time 2 are lower than scores at time 1, then that means we're predicting our differences to be positive. Okay, so if this number is predicted to be higher than this number, then the differences are predicted to be positive. So with hypothesis testing, we're going to use D bar cap. D bar cap, in this case, is predicted to be greater than 0. All that means is that I'm predicting the differences to be positive. 120 minus 100 is a positive number. I'm predicting the differences to be positive. That's what the D bar cap greater than 0 means. The null hypothesis is going to be the opposite. In this case, D bar cap is less than or equal to 0. So the hypotheses are going to be framed in terms of D bar cap, whether that is predicted to be positive or predicted to be negative. Step number 2 is going to be the comparison distribution. Okay, so the comparison distribution, it's going to be a t-distribution. I'll draw it over here. It is based on a degrees of freedom of 2. Degrees of freedom equals 2, or n equals 3, meaning there's 3 individuals in the study. The degrees of freedom is 2. And kids, my dog's about to start barking. So Just take a second. There was a reason we had him outside. Nico, come over here for a sec, bud. Nikki. Nikki, come. Nick, go ahead. Okay, sorry about that. So the comparison distribution is a t-distribution based on degrees of freedom of 2. Every t-distribution differs as a function of the n, the sample size. Remember, the sample size minus 1 is simply the degrees of freedom. Okay, step number 3, the critical value, or t-critical. Importantly, the sign of t-critical follows the sign of d bar cap. So the sign of t-critical follows the sign of d bar cap. D bar cap is predicted to be positive, therefore t-critical is predicted to be positive. I didn't give you an alpha, but I can give you that alpha of 0.05, which is standard. And if we look up the t-critical, here, we're going to see the same exact situation we found last time. 2 degrees of freedom, it's a one-tail test, because we're making a prediction in a specific direction, and the answer is 2.92. So t-critical, just like in the last example, is 2.92. And everything to the right over here is your alpha region. Okay, step number 4, we're going to get t obtained. So t obtained, or t equals d bar over s sub n. Okay, so it's going to be the average difference divided by S sub n, which is the standard deviation of our comparison distribution. Okay, so to do this, we're going to use the same kind of process we used for the one sample t-test, very similar. We're going to figure out the differences. 120 minus 100 is 20. 200 minus 160 is 40. 140 minus 100 is 40. You can see whatever this diet is, everyone lost a ton of weight, so this is a good diet that I invented here. So those are the differences. The D bar is the average of the differences. So that's actually going to be 100 divided by 3, which is 33.33. Okay, now we have D minus D bar. Yeah, we have D minus D bar. So this is negative 13.33. Let me see if I get that right. 20 minus 33.33 is 13. Negative 13.33. I'm going to have to redo my distribution somewhere. 40 minus 33.33 is 6.7, or 6.67. This one is also 6.67. Next, we're going to square these. So D minus D bar squared. 13.33 times 177.69. $6.67 times 6.67 equals 44.49. And also here 44.49. Okay, so now the process is very parallel to what we've done before. We're going to do sigma d minus d bar square, which is the sum of that column. 177.69 plus 44.49 plus 44.49 is 266.67. Sigma square equals sigma d minus d bar square divided by n minus 1, which is 266.67 divided by 2, which is 133.34. Okay, I'm going to compute S. Again, not that we're going to use that in the immediate, but we're going to hold on to it because we'll need that for effect size. S is the square root of S squared, which is 133.34 square root. So S equals 3.65. Next, we're going to get S squared sub m, which equals S squared divided by n, which is 133.34 divided by 3, which is 44.45. And then finally, S sub m, which is the denominator for our t, is going to be the square root of S squared sub m, so 44.45. Square root of that is 6.67. Ooh, so that was a long haul. But let's take a look over here. You remember that t obtained equals d bar over S sub m, which is 33.33 divided by 6.67. My calculator's saying 4.50. Is that what you got, Dana?
No, I got 4.99.
997?
Oh, sorry, yeah.
Yeah,
You're
so
right.
with the crazy rounding on that one, kids. Yep, but there we go. So there we go, we got 4.50. Now, let's take a look. I'm gonna do a giant erase right here, kids. Hurts me more than it hurts you. And what we have is this t distribution. Remember, t critical is 2.92, and t obtained is 4.5. Okay, so you can see here's the alpha region. T obtained was more extreme than T critical, suggesting we support the research hypothesis. In this case, that means we would say the diet that we implemented on average worked. People on average tended to weigh less at time 2 than at time 1. So that's how you do the within group t-test. A final detail before we finish with this chapter has to do with how to compute effect size. So we still have Cohen's D. We now have a different, slightly different version of Cohen's D. It equals D bar over S. Dan, is there any
Did you erase
chance?
it? I did not write it down. I could figure it out if you want.
Dang. I hadn't really thought too much about that. Remember, I put it in a box and everything?
Gosh,
Oh boy.
I'm trying to think of what the.
I erased the whole thing. Hey, you know what? It's coronavirus time, kids. These are austere conditions. We computed S before. I know you saw it. I know you have it in your notes. Cohen's D equals D bar, which I think was 33.33. That one I have memorized. Divided by S. And the answer there is your Cohen's D. So is that a slightly disappointing ending to this chapter? Perhaps. But in either case, this has been Stats or Glenn.